Yeah, thanks for inviting me to this workshop. I was really hoping to be there in person, but then there was a COVID case in my daughter's daycare and I had to cancel all my plans. So unfortunately, I'll be remote for this week, but I do still want to tell you about this topic, which I hope can be an interesting kind of probabilistic substrate for building causal models and doing causal inference. And so the topic of my talk is tractable probabilistic circuits. By the way, I don't really know in this setup if it's easy to interrupt with questions, but if it is, please feel free to do so. Okay. All right, so what do I want to talk about? So first of all, what are these tractable probabilistic circuits? You probably haven't really seen them before. Then I want to convince you very briefly, just from a machine learning perspective, that these models are quite interesting and very powerful. But of course, this is not a machine learning workshop, and I mostly want to talk about the theoretical properties of these things, in what is their expressive power, circuit lower bounds, and how far can we push tractable inference. And so those would be the algorithmic aspects of these representations. Okay, so first of all, what are these tractable probabilistic circuits? So here's a little bit of an alphabet soup of different generative models, probabilistic models that are around. Very famously, things like GANs, variational autoencoders, more traditional things like Bayesian networks, vector graphs, etc. And it's a little bit of an alphabet soup. And so the way that I like to distinguish these different things is in terms of tractable versus intractable models. The tractable models are relatively simple kind of models, but they can be very powerful. But their simplicity allows you to compute, for example, a marginal probability, a partition function, exactly in polynomial time, often in linear time, in the size of the representation. And then you have the intractable models, where often the only thing you can really do is sample from the model. And so there's a lot of tractable models. It's kind of impossible to really have the overview of the whole literature. Some product networks, thin junction trees, DPPs, arithmetic circuits in the UAI community, etc., etc. And so what I would like to kind of summarize for you is that essentially all of these tractable models that allow you to compute a marginal probability, a partition function, they can really just be understood as being very simple computational graphs. And so we refer to kind of this whole family of tractable models as probabilistic circuits. So this is what they look like. They are very similar to neural networks in that they form a computation graph. They're also very similar to arithmetic circuits in the theory community. At the input, you have some simple distribution, let's say a univariate Gaussian, a Bernoulli, or really anything you want, something really simple that allows you to compute what you want efficiently, let's say a marginal probability. Then the one building block is mixture models, sum nodes. So these sum units, they take two other circuits as input and take a weighted average. That's your standard mixture model. And then there's a very basic notion of factorization. You take two probabilistic circuits that are over different random variables, and you multiply them to get the product distribution. And then you make a little bit of an inductive leap, and you just construct directed acyclic graphs with these types of computational units. And then, of course, you can really think of them as neural networks having millions, hundreds of millions of these computational units. Okay, why do we call them tractable models? Well, they're tractable because we can compute a whole bunch of things exactly and efficiently. The simplest thing you would like to compute is the likelihood function. You would like to know the probability of some feature vector over here. And the probability of this vector here. So what we do is we ask all of the inputs to our probabilistic circuit, what is the likelihood of all of the data? You get those numbers. These are the likelihoods, densities or probabilities, it doesn't matter. And then you just sum them, multiply them, and in the end you get that the likelihood of the model given this data point is 0.75. Okay, so very simple feed-forward evaluation. But what we really want to do is compute things that are more challenging, like marginals, right? And so these are traditionally intractable on graphical models and really almost anything you can think of. So here we'll have to invoke some really basic properties. They're very natural, but they're required if you would like to compute a marginal probability. The first property is called smoothness, and it really means that when you have a mixture model, it doesn't make sense to mix two distributions that have disjoint scopes, disjoint sets of random variables. If you mix two distributions together, they must be talking about the exact same set of random variables, otherwise a mixture model is ill-defined. So that's the property of smoothness. And then more interesting is the property of decomposability. Decomposability says that when you take a product distribution, the component distributions have to be independent from each other. They must have a disjoint scope. And of course, this makes sense. Products you can only take over probabilities that are over different random variables. This property is also very natural from a theoretical perspective, right? In the arithmetic circuit literature, this is called syntactic multilinearity. And with these two properties, now you can compute a marginal. Here's how you do it. You can just think of it as a recursive kind of way of simplifying an integral, right? If I need to compute an integral over a sum node, because of linearity, I can just take the weighted average of the integrals of the children. Okay, so that's pretty straightforward. If I have a product node here and I need to compute some integral, because of this decomposability, I can really just take the product of the integrals over the three different children, all restricted to the scope that they are talking about. Okay, so all these integrals, they just decompose into easier ones, and I can compute my integral in this kind of top-down recursive manner. And this gives you a very nice dynamic programming algorithm where if I now want to compute some marginal probability of x2 and x4 having some value, marginalizing out x1 and x3, what I do is, well, I would have to compute the integral over x1 and x3, and that ends up being 1 in a distribution. So all of the input nodes that are marginalized out become 1. All the other ones, they evaluate to their likelihoods. And then what I do is I take sums of products of sums of products, and I get my marginal probability at the output. I hope this makes sense. Otherwise, again, feel free to interrupt somehow. I'm not sure how I will hear, but I hope to hear someone ask a question. Anyway, okay. So this is why these models are tractable, why we're interested in them. So the next question is, well, if I can compute a marginal probability, then surely these probabilistic models are very simple. Maybe they're like naive Bayes. They're kind of they have a limited capacity. They're really just too simple to really fit a interesting data set, right? So that would be your immediate gut feeling. And so the next couple of minutes, I just want to argue that, yeah, this is not the case. These are actually quite powerful models because they can really have the power of a deep neural network in the sense that they can have a gigantic number of neurons and really fit data very well. So here's a quick summary of how one could learn such a probabilistic circuit. So the first question is, where do you actually get this structure from? You need to have this smoothness and decomposability. It's not as straightforward as just adding a few layers to your neural network. So you have to do a little bit of extra work, and this is how we do it. This is a model that we call hidden Chow-Liu trees. We start from our mutual information matrix between all of the random variables estimated on the data. From this, we just do the standard 70-year-old learning of Chow-Liu trees, right? We learn a tree-shaped graphical model that best fits this data. And then we turn it into a hidden variable model. And so this is crucial to increase the capacity of these Chow-Liu trees. So now we take exactly the same structure that we learned before, but we turn all of these variables that were the pixels in our image into latent variables. And all of the pixels of our image are now just emitted from these latent variables. Very, very similar to how you take a Markov chain and turn it into a hidden Markov model. So this is still a graphical model, right? So this is old school stuff. So how do we turn it into a neural network? Well, if you do inference on this graphical model, you're going to do a bunch of sums and products. Your favorite inference algorithm on this tree-shaped graphical model, message passing, it's essentially doing sums of products of sums of products. You can turn this into an equivalent probabilistic circuit, and now you have a neural network. And now that you have this neural network, you can just train it. We're using mini-batch stochastic expectation maximization. You just train it like a neural network, okay? And that means you can really scale that up on the GPU to 100 million parameters. Okay, so that's one way to learn these models. Here's a quick summary of trying to convince you that this is really a powerful tool. So here we look at an application which is image compression. I'm sure you're familiar with the basic concept, right? You encode the data in a bit stream and you decode it. And of course, if you have a probabilistic model to do the encoding, you can do entropy coding, or you can, for example, do arithmetic coding to really just get the lowest number of bits here to represent your image to compress it maximally. So this, in general, if you use a machine learning model to do this, this is called neural compression. And so what we're doing here is using a probabilistic circuit to compress MNIST images. And so the first thing that should surprise you is that if you just train this model that I showed on the previous slide, it's really expressive. And it actually gets a state-of-the-art likelihood on MNIST. So it outperforms the variational autoencoders, hierarchical variational autoencoders, flow models. It outperforms really anything else that I'm aware of in fitting a density to MNIST pixels. And this is the full MNIST, right? So no binarization, no quantization, just full MNIST. And then what's also really interesting is that if you want to do compression, it has to be fast, right? You cannot really afford to spend like a minute decompressing your image. And so this is really tricky. If you have a powerful probabilistic model, you need to compute a lot of marginal probabilities to do arithmetic coding to do your image compression and decompression. Essentially, you have to compute what is the probability of the next pixel values, the cumulative probability, given all the previously sent pixels, right? So that's a lot of different marginals you have to compute all in sequence. And so what's in general true about these probabilistic circuits is that they're so well behaved that typically these things end up having some nice algorithmic solution. And here the summary is that instead of having to compute this marginal query for each pixel, linear in the dimension of the image, you can actually just have this logarithmic factor because a lot of the computation can be amortized. And the summary is then that you get state-of-the-art compression rates on MNIST, eMNIST, close to state-of-the-art on fashion MNIST, etc., compared to all of these baselines. But you also get this 5 to 40 times faster than neural network methods. Okay, so this was kind of a whirlwind tour. You can also combine probabilistic circuits with bijections, flow models, and also get really good results on ImageNet density estimation. All right, so this was kind of a whirlwind tour of like the machine learning side of things. So first the basic representation, then the machine learning side of things. Hopefully now you're convinced that okay, these models might be worth of some more theoretical study because they do seem to have some capabilities, right? And so here's where I want to get into the theory of what can these models represent. And also, how far can we push this tractable inference? I told you we can compute marginal probabilities, likelihoods, but there's so many more questions you could have of a probability distribution. And what do we need from these models in order to compute things like a KL divergence exactly and in polynomial time? Okay, so first question first. Well, these probabilistic circuits, they kind of can do some product computation. Right, so if you have your junction tree algorithm, your kind of message passing on trees, you have some product networks, etc. They're all really just doing the same computation. And so a natural question is, do we know of any probabilistic models that are tractable that we can compute a marginal probability for, yet that are not captured by these probabilistic circuit computation graphs? And so here. There was a few years ago, there was just this one model that kept bugging me because it is a tractable model called determinantal point processes. And we didn't know how it related to probabilistic circuits. And so briefly, a determinantal point process, it's really just this matrix where if you would like to compute a probability for a particular world, for example, I would like to know the probability that x1 is true, x3 is true, everything else is false. Then I just take the subdeterminant of the first and third row and column. Okay, so the red numbers here, their determinant up to a normalizing constant is the probability of this particular world. And so, of course, this determinant is efficient to compute. And so this is a tractable probabilistic model. These are really nice. They're tractable for likelihoods and marginals. They capture global negative dependence in an elegant way, and they're, of course, used a lot for capturing diversity in recommender systems. And so the question here is, well, you have these probabilistic circuits that actually include all graphical models that are able to do exact inference. And on the other hand, we have determinantal point processes. How are they related? And one part of the answer is really easy. there are models, there are distributions that live at the intersection of the two of them. For example, if your determinantal point process is a diagonal matrix, fully factorized distribution, it also has a probabilistic circuit representation. But the real question is, are there determinantal point processes that cannot be captured in this framework that I just showed you? Okay. And so we started looking first at, what is the easiest theorem to prove is, well, you take the type of probabilistic circuit. I mean, it's a whole family of different models. You take the type of probabilistic circuit that is the most restricted one in its properties, but also the most tractable one that you can compute more than just marginals with. These are called probabilistic sentential decision diagrams. And so it's pretty easy to prove that, with probability 1, a random DPP is not going to be having a tractable representation as a PSDD. And then we start kind of dropping some of these properties. If it's just a syntactic multilinear PC with positive parameters, no, impossible. If you have other properties, I won't go into details, no, impossible. Some product networks, perhaps the most famous type of probabilistic circuit, also they cannot represent certain DPPs efficiently. And if you have syntactic multilinear probabilistic circuits, so decomposable PCs with negative parameters, then the question is open, right? So we can add this to the open question session tomorrow, although it's really just as hard as proving, circuit lower bounds with negative. So it's essentially a very difficult problem for the whole theory community. So I don't really think this is one we can easily solve. Okay, so the summary here is that, these properties, theoretically, they do actually limit what you can represent. And specifically, DPPs are the type of model that you cannot easily represent in these probabilistic circuits. So what we then try to do next is come up with some representation that kind of unifies the probabilistic circuits that we knew with this determinantal point process model. And this is tricky, right? Because the probabilistic circuits are computation graphs. DPPs are kind of determinant-based, kind of matrix-based models. They don't really speak the same language. Until we realized that, there is one language that is in common between all of these things. And it's in fact the language that a lot of theoreticians use to study probability, right? And so that's the language of probability generating functions. If you're not familiar with these, I'm sure most of the audience is a bigger expert on these than I am. Essentially what they are these polynomials that kind of capture the probability of a possible world as coefficients of these terms here. Specifically, this term here, where the z appears, all of the z's appear, corresponds to the world where all of these features are set to true. It has 16% probability. Okay, and now, of course, these probability generating functions are often used to prove theorems, right? They're a theoretical tool. I'm not aware of them really being used as a machine learning model per se, right? And so the little bit of a leap that we made was to say, well, let's take these generating functions, which, if they're just flat functions, they have as many terms as there are, possible worlds, right? These are just theoretical tools. And let's really think of them as data structures, as little directed acyclic graphs, right? I can take this generating function, I can rewrite it in this form, and it's still the same probability distribution. So then it's not much of a leap to say, well, if we can do this, why don't we just write them as computation graphs, as something that looks similar to a probabilistic circuit? So this is really just the same as a probabilistic circuit. The only difference is that at the inputs now we have constants, and we also have these variables here that come from the generating function syntax. Otherwise, this is just representing exactly the same generating function we had before, but just more compactly as a circuit. I guess you can see how, all of the terms here show up in the circuit. So now we have some kind of common language, perhaps, between the two, because it's very well known that a determinantal point process also has a generating function, and it is described in this way. It's really up to a constant, a determinant of this matrix here, which is the matrix L, the parameters I showed you earlier. We had to take these subdeterminants here, and then this diagonal matrix of these z's here. This determinant has a arithmetic circuit. you can find some theory papers that show how to construct it. And so bottom line is you can now take these DPPs and you can turn them into these probabilistic generating functions represented as circuits. So probabilistic generating circuits of polynomial size. And so that means that now we have a representation that captures DPPs. And similarly, you can take a probabilistic circuit and you can write it in this PGC syntax. But we're not done yet, right? The whole point of probabilistic circuits is that we have a representation that allows for tractable inference, for example, marginals. So how is it possible that if you give me a gigantic probabilistic generating function as a circuit with 100 million nodes, that I can even compute a marginal probability there, right? It's not obvious. I mean, clearly the generating function represents the right distribution, but how is it even possible to compute a marginal probability? So let me illustrate how this works. Let's say I want to compute the probability that x1 is 1, x2 is 0, et cetera, et cetera. So the way that we'll evaluate the circuit to compute a marginal is that whenever the variable is observed to be 1, we replace it by some symbolic t, okay? If it's set to 0, we replace it by 0, and otherwise we replace it by 1. And so now through the magic of generating functions, what this really means is that we are now computing this other polynomial here. It's a polynomial in t. And its degree is up to the number of random variables. And the probability that we're looking for of the world corresponding to these inputs is just the leading coefficient of this polynomial. Okay. Let me give you just a simple example of how this works, right? So I want to compute specifically this input, this marginal probability. So I input 0, 1, and this symbolic t, depending on the query I have. I evaluate my polynomial, it's 0.16 t plus blah. And indeed, the 0.16 is the probability of these two worlds, which is if you sum them up, is the probability of this marginal, okay? And so this can all be done in time polynomial in this size of the circuit. Okay, if you're a machine learner in the audience and you're like, oh, this is a lot of theory or almost theory, I care about my bottom line machine learning performance. If you now take the standard data sets that people use to train determinantal point processes and you train this generating function model, which you can now kind of make up some architecture for it, it's suddenly has much more flexibility than just the DPP, then you get state-of-the-art likelihoods on 11 of the 15 standard data sets used in this field. So this also works well as a machine learning model. Okay, so that was kind of my brief intro on like what's the circuit lower bound kind of representation power property of these models. And then for the remainder of my talk, I want to kind of briefly go over some interesting algorithmic aspects of query evaluation on these models. Specifically, can we compute something more difficult than just a marginal probability? Okay, so now we're going back to the probabilistic circuit world. And we would like to compute things like KL divergence, because obviously this would be super useful. For example, if I want to do variational inference, but in many domains, you would like to compute a KL divergence. This is the definition. And the approach we will take is, as always, as throughout, what we've done throughout this talk, is just treat these problems as computation graphs. So now I can really just think of this KL divergence as being this pipeline, where first I have to take this quotient of two distributions, P and Q, okay? Then for the result of that quotient, I have to take the log of this function, element-wise, right? Then I have to take the element-wise product with the distribution P, and then I have to compute an integral. And so far, the only thing that I told you how to do is compute this integral, right? Computing this integral was, computing the marginal probability. In this case, it's not necessarily a probability, but the same algorithm applies. You can compute an integral on these circuit representations that are decomposable and smooth. But how do we figure out whether we can take this quotient, the log, and the product? And moreover, if we can do so, then there's a whole bunch of other stuff we can compute, like cross entropy, et cetera, that are really just the same building blocks over and over again. And so here, without going into too many details, what we proved is that if your input distribution is smooth and decomposable, which are the properties I already showed you before, but it has this other property called determinism. You might notice as unambiguity in the theory world, et cetera, et cetera. It basically means that when you have a mixture model, the mixture components are disjoint in their support. If you have this property, then yes, you can take efficiently the log of this distribution and get this new circuit, which is no longer a distribution, of course, it's just a function, but it's still smooth and decomposable, and therefore we can still compute an integral here. And again, without boring you with all the details, you can do this exercise for a lot of these operations, for products, powers, quotients, logs, exponents. And what we did here is find the properties that are required of the input in order to get nice properties of the output. What do we need on the input so that on the output we can still compute, let's say, an integral. And then we also proved that when you don't have these properties, essentially it's impossible to do these operations on the distribution. So these were kind of the basic building blocks of how you combine circuits. And now you can really have fun finding in your textbooks your favorite questions. Can I compute a cross entropy? Can I compute a KL divergence, et cetera, et cetera? Then you know the properties necessary to do all of these arithmetic operations. And then we also proved that if you don't have those properties, things are computationally hard. Okay, so this is kind of a quick way to hopefully entice you to look into these information theoretic queries on distribution and think when can we actually compute them, when are they tractable, because now everyone just assumes that you'll have to sample your way through these types of problems. Another very difficult question is how to do marginal map. So in marginal map, the goal is to find the most likely state of a subset of your random variables while marginalizing out a other set of variables and then also maybe observing for a third set of variables their value. This is essentially what you want to do if you, let's say, generate text from a language model, if you want to do, labeling of pixels in an image in a latent variable model, et cetera, et cetera. This is really the task that a lot of machine learning downstream is about. Unfortunately, it's a really difficult task computationally. It's NP to the PP complete for graphical models. It's NP hard still on tractable graphical models like naive Bayes models even. So this is a tricky problem. And so here, maybe we don't really hope to find a tractable representation that you can compute any kind of marginal map query on. That seems like a bit of a stretch. But we can still use the tractability of these models to actually come up with interesting algorithms. And so one such interesting algorithm is the one here. And the observation is that if you try to do these optimization tasks on distributions, like marginal map, then really a large part of your model becomes irrelevant to the computation you need to do. For example, if I am interested in states that look like this, then this part of my circuit is relevant. The other part is completely irrelevant. Whatever the parameters are here, it doesn't really change what would be the marginal map. So the goal here is to really find which part of my model is actually relevant to the query and then simplify the model. And again, without going into too much details, this gives you a state-of-the-art algorithm for marginal map on probabilistic circuits and graphical models that are turned into probabilistic circuits. Okay, final kind of interesting connection is to kernels, which I hope will be of interest to some folks in the audience, some of the theoreticians. So a lot of applications of kernels involve computing an expectation over two data distributions of the kernel. And so again, the standard trick you do is, when you build these algorithms around probabilistic circuits and other circuits, is you just think of any computation as being a circuit-based computation. And so also here, we now take our favorite kernel, and then we just turn it into a little computation graph, sums of products of these very simple univariate input units. And what we show is that with smooth and decomposable probabilistic circuits, we can also compute this expectation in polynomial time of these types of kernels. And so this then allows you to do some really cool applications. For example, if you have a support vector regression model that looks like this, where you use the kernel essentially as a regression model, you can now actually impute over missing features in your predictions using a probabilistic circuit and compute the expectation of your support vector regression model expectation over all of the imputations of your missing features. And so this is not something you can do standardly with support vector regression. Similarly, if you're into Stein variational inference or the Stein operator, it also involves an expected kernel matrix, where you can actually do some of this stuff exactly in closed form using not just samples, but using circuits to compute expectations of these kernels. All right, so that was the big overview. So I hope that I at least got across kind of what are these probabilistic circuits, as you know, their simple syntax and how you compute a marginal. I hope I convinced you that these are actually really good machine learning models, even though this is not a machine learning workshop, but then that there's interesting connections to the theory community, specifically to the arithmetic circuit, and specifically the multilinear arithmetic circuit lower bound community. But then also that there's interesting new algorithms that one can derive by looking at distributions and functions really as computation graphs and doing operations on them, assuming properties. All right, thanks for your attention. And also thanks for all the folks who did the actual work on this.
Questions for, can you hear us? Okay.
Yeah, I can hear you.
Yeah. Question?
Yeah. Nice guy. Can you hear me?
Yeah.
Oh, yeah. So for the image data, you suggest combining the model with a normalizing flow. So how does it compare to just training a normalizing flow by itself? Like, are there advantages of this versus just using a normalizing flow?
Yeah, good question. So let me quickly find the slide. So we actually compared to the normalizing flow directly. And so, no, this is too far. Sorry, don't know the slides. Oh, so this is the slide you're asking about. So here, IDF is a normalizing flow, discrete normalizing flow model. And so essentially what we did is, so normalizing flows similar to VAEs, they have a latent space, which is actually a very, very simple tractable model, like a fully factorized Gaussian or a fully factorized distribution, or complete product distribution, right? And so what we did here is we took IDF and we replaced that very simple latent space by a non-trivial probabilistic circuit in the latent space. And this is PC plus IDF. And the summary here is that, yeah, if you actually use a very expressive tractable model as your latent space, you get a significant boost in these flow models. And yeah, and so this is a direct comparison of the flow model, two flow models with a simple latent space and with a probabilistic circuit latent space. Does that answer your question?
Yeah, but it doesn't have the, like, you can't compute marginals or anything, right? That's the...
Yeah, so that's a good point. So in this PC plus IDF model, you cannot compute a marginal because the bijection of the flow model actually ruins that ability. But it turns out that if you want to do image compression, you don't really need the ability to compute the marginals here. You just need to get, because you know, you can essentially compute the marginal in the latent space through the bijection, and that's enough to do image compression. If you want to compute marginals in pixel space, then here you're out of luck. So here we're kind of walking a fine line of tractability where we still are tractable enough to do image compression, but we do lose some of the power. And in exchange, we get state-of-the-art, or maybe not state-of-the-art, really good image compression and likelihood. Yeah.
Questions?
Oh, so I have one. Do you know of any? So you said that math in inference was hard under these models. Are there any kind of conditions under which like approximate math inference could be possible?
Yeah, that's a good question. There might be, and I'm not aware of them, but I'm not aware of any. So there is a condition in which certain types of map inferences are possible. So if you have a certain order on your variables and you restrict yourself to map problems that are you know, always the same set of optimization variables and the same set of marginal variables, then there is a tractable model for it, which is essentially a probabilistic circuit with a particular variable order. But that's really not a real solution, because essentially, you're restricted to just essentially one query. You have a tractable model for one specific query, and it's not really a general solution. In terms of guarantees, approximation guarantees, I would love to know if anyone knew about a model that had those. Yeah, I don't know.
Oh, I'll say the reason why I asked is about the DPPs. I think there's some submodularity. And so you can do approximate map inference on those, which is what made me think about that.
Oh yeah, good point. So this is for full, what we call full map. So that there we find the most likely state of all of the variables, and then yes, you have the approximation guarantee. So this is marginal map, right? But I guess in DPPs that would also have the same approximation guarantee. Yeah, I'll have to think about that one. Yeah, it's not obvious to me that marginal map has guarantees on DPPs, but yeah, we can talk about this offline maybe. That's interesting. Is it clear what the distinction is between marginal map and map, right? So in map, it's really
Yes.
all of the, yeah, okay.
Oh, yes. And by the way, we can talk offline more about it, but I think marginal map is possible for DPPs. But we can talk, that's my intuition, I think, because the DPP is closed under, yeah. Anyways, we can talk all the time.
Sounds good, thanks.
Anybody else? Okay, so we are exactly on time for our break. The next talk will begin at 10:40. It's a good deal.